midterms graded. I'll have them done by Thursday, promise. Today's lab, we're gonna do an esterification, I believe, of benzocaine. And then after that, it's PCR. And then that's a 2-part lab, so we set up all the reagents and put it in the thermocycler and let it do its thing. And then the next lab, we run some gel, we make some gel and run some gels. And so may not take the whole lab period, but we can't do it all in 3 hours. So we'll split it up. And then after that, there's one more lab period, which I want to use as a final preparation. And that's it. So we've got 4 weeks left, I think.
Yeah.
It's a month, but it's going to go by quickly. So today we're going to talk about amines. I didn't get this far last year, so it's a little bit uncharted territory. So we'll see how it goes. But I did try to incorporate, since I had to make these slide decks new, I tried to incorporate a little bit of the OpenStax, because I know that Sean had used that textbook this time instead of the Klein. So there are a few in there, but I like the aesthetics of the Klein book better.
Yeah, the graphics are nice.
The graphics, you get what you pay for. And I just kind of threw this in here because this is a fun little periodic table as seen by organic chemists. So hydrogen, of course, is carbon's buddy, and our first column of things, don't get wet, right? Don't put sodium metal in water, and then boring things, and then really important catalysts and valuable transition metals, and then fake elements made up by commies. Who cares? Weird nukes. America, Einsteinium, named after geniuses, but then I kind of disagree with this. I guess these are okay. Those are the halides, right? So
Pretty important.
we could argue that halides are pretty important, right, for a lot of the reactions that we've been talking about. Lazy elements, and then need these to live, right? So amines are absolutely essential for life, right? So nitrogen, carbon, oxygen, these things, sulfur, these things are crucial. And amines in particular have a profound effect on our biomolecular makeup, as well as certain drugs that we take, compounds naturally from plants or synthetically made in a lab. And so we'll talk about that. For today, we're going to get into some of the properties of amines, how they act as nucleophiles and are basic. Okay? And it turns out they behave similarly when in a physiological pH as carboxylic acids. If you remember last week we talked about, I think it was last week, no, I guess maybe 2 weeks ago now, Henderson-Hasselbalch equation and how pKa will drive it toward one side or the other at equilibrium, and carboxylic acids actually exist as carboxylate ions, meaning they lose that hydrogen on the OH group at physiological pH. Amines do the same thing, only instead of getting a negative charge, since they're basic, they accept protons, right? And so they end up getting a positive charge. We'll go into naming these, and then we'll get into how do we make amines, all right? And then in this OpenStax, I do like how at the beginning they have, why are you learning this chapter? So I put that in here too. Of the groups that we've talked about, the carbonyls and the amines are the most abundant. Okay, so not just physiologically important, but because they are physiological, we find them in all living things, right? And have a very storied and rich chemistry in terms of exploiting these compounds in pharmaceutical approaches in particular. Our proteins, amino acids, drugs, all of these things, enzymes or proteins, right? So biologically, amines are essential. And we'll talk a little bit about what happens when they compete with each other and have adverse consequences. All right. So it turns out that we can take ammonia and easily turn it into an amine. Okay. So we can make it a primary amine, a secondary amine, or a tertiary amine. And what we'll talk about later on, we can even make this a quaternary. Obviously, it doesn't want to be a quaternary because nitrogen prefers to have 3 bonds to be most stable, but we can make things like quaternary ammonium salts, which are used as antimicrobial agents in particular. So here are some examples of amines that are abundant in nature. A lot of these are extracted from plants that are called alkaloids. They're called alkaloids because they're alkaline in nature, right? And alkaline means basic. And as I mentioned, amines can be nucleophiles and have basicity. That's an important characteristic of it. So what drives these alkaloids to be basic is the presence of these amine groups. And so things like triethylamine, nicotine, cocaine, caffeine, it's not on here, but definitely morphine, all of these things have an amine group embedded in there somehow. Okay? And it's the amine group that is driving a lot of the activity and the active ingredient portions of these compounds and how they interact with us. Okay? Here's a few other examples of how they are abundant in nature, specifically in the way that they affect our neurochemistry, right? We're all familiar with adrenaline, the fight or flight response, that surge that we feel when we're stressed. We know about noradrenaline and how, well, maybe you do, that it's a little bit less common, but it leads to things like dilation of our airways. So a lot of times these work in conjunction with each other. So if you think about the need for adrenaline, if you're in some kind of environment where your adrenaline is coursing through your body, you probably need to breathe. Right? We always need to breathe regardless, but if you're in a fight or flight response, you're going to be taking in more air. And so your heart is also going to need to beat faster, right, to pump blood to get that air to all of our extremities, right? And so these work in conjunction with one another to help us survive. And then dopamine, that's often linked with things like pleasure, and can also be involved in certain fine motor skills. A lot of these things are actually produced in our gut in conjunction with our microbiome. So the bacteria in our gut make metabolites from the food that we eat that they break down, and a lot of that is synthesized by our gut microbiome. Okay, so it's important to have a robust microbiome to have a appropriate hormonal balance, if you will. Okay, so as I mentioned, amines are basic and they are nucleophilic. So functioning as a base means that they accept a proton, right? To be nucleophilic, they also need to attack a carbon group and attach itself to that, kicking off something in the process, right? And the reason that this takes place is because of the lone pairs present on these amine groups. Okay, so the lone pairs allow for that proton to hop aboard, right? The lone pairs help it attack the carbon. Okay, and being basic is one of the most important properties. Okay, it's a stronger base than alcohols and ethers, and it can be protonated even by weak acids. So a strong acid completely dissociates, right? Weak acids don't dissociate as much. They hold on to that proton. But because an amine is such a basic functional group, it can force those protons off of an acid that doesn't necessarily want, in quotations, to give that off. So if we had a base like triethylamine, which is one of those right here, right there, triethylamine, or that's trimethylamine. That's fine. Trimethylamine, triethylamine, whichever, doesn't matter. Right? And we put it in with, let's just say, acetic acid. So, let's switch the other way. We can all agree that acetic acid is a weak acid. Right? Okay, it's vinegar. Right? So we can drink vinegar. What can happen here, right, is that it can take on that proton and essentially deprotonate this. And then you end up with so weak acid, but in the presence of something that's an even weaker acid, right? If this is a strong base, we can all agree that it's going to be a really, really terrible acid. It's not going to want to kick off any hydrogens, and so it can end up deprotonating. Now, as I mentioned, like with carboxylic acids, at physiological pH, it's going to predominantly exist in this form. So here are these arrows. Have you seen arrows like this before? Okay. So this is showing that at equilibrium, it's going to be predominantly to the right in this case. All right. And that's largely due to the fact that it is a strong base. So it's pKa. It's going to be,
Pi.
what's that?
Have a high pKa?
It's gonna be high, yeah. It's like 10 something. Okay. And so as a result, when you put it at a pH of 7.4, right, it's going to drive it to this form here. So with carboxylic acids, we said that it was, if you remember, right, predominates this, right? Here predominates in the opposite direction, right? The acid's gonna kick off that hydrogen, have a negative charge. The ammonium that's formed is going to, or this quat ammonium salt is going to have a positive charge. Okay, and that's going to be the favored form at physiological pH. So in our bodies, that's how it's going to look. Okay. Now, because of these properties, these nucleophilic properties, and these basic properties, it can be challenging when we design drugs from, basically from plants originally, these alkaloid-derived pharmaceuticals. It can be challenging to see how they break down or don't break down. So this drug here, Allegra, yeah. So an antihistamine. Okay. Initially, it was terfenadine, which is this molecule with an R group. The R group just being a methyl group. Okay. Turns out that when certain patients were taking terfenadine in conjunction with antifungals and antibiotics like antibiotic erythromycin and antifungal, some kind of keto-based antifungal, it would negatively react and lead to cardiac arrhythmia, so an irregular heartbeat. And what they found out was that the problem was that when taken in conjunction with these other drugs, this wasn't getting broken down, it wasn't getting metabolized. And so it was accumulating in the body and leading to those negative side effects. And so pharmaceutical researchers started looking at metabolites of this terfenadine, meaning let's see what this is broken down into and test those to see if they have a similar consequence. And it turns out that fexofenadine, or as what we know of as Allegra, the R group is a carboxylic acid instead of a methyl group. So what happens is terfenadine here with a methyl group gets metabolized and essentially replaces just the methyl there, or this ethyl group, with a carboxylic acid. So oftentimes we think about metabolizing something as taking it and making it more simple, right? In this case, we're not making it more simple, we're actually putting more atoms on here, right? But that is still considered metabolism. And funny enough, it turned out that that did not cause arrhythmia, and that this wasn't even the active drug. It turns out that this functional group here was the active ingredient in that whole molecule. And so terfenadine was actually more of a what's called a prodrug, so something that then gets broken down into the active form. So all this time they were using something that was inappropriate, right? And so by this point, they could use this in conjunction with those antifungals and antibiotics. It wouldn't accumulate, and it would be absorbed and properly metabolized further beyond that. Okay. And look what's in there, right? There's an amine group in there. There's also some unanticipated beneficial side effects of things. So, diphenhydramine is also an antihistamine. Okay, and so a drug company decided that they would combine it with 8-chlorotheophylline, which is basically just a chlorinated caffeine molecule. So that's my favorite molecule right there. And so the idea was that if we put these together, we can make a non-drowsy antihistamine. Right? Turns out that the drowsy effects of this diphenhydramine were superseding any kind of beneficial effects of the caffeine. So they were still getting drowsy. All right, so it wasn't effective in its anticipated design. But there was an interesting side effect that was observed in some small cohort of patients that were in this study. They were reporting that, my whole life I've been carsick, and now for whatever reason, I'm having much less symptoms of car sickness. And so they said, okay, right? That's how scientific discoveries are, the majority of the time, found. Not by intended purpose, but by accidental things. And instead of saying, okay, well that's weird, whatever, they say, that's weird. Why is that weird? And is that reproducible? And can we exploit that? And sure enough, they put these together, and instead of using it as a non-drowsy antihistamine, they use it as dimenhydrinate, or you guys may know it as Dramamine, which is taken for to prevent seasickness, car sickness, that kind of thing. And this is an amine, right? Group. Lots of amine groups. Okay. So it really depends on how these things interact and what they're combined with in terms of conferring certain properties. Here's an interesting one. So, solanopsin, that is a compound that is secreted by fire ants. It's what makes the fire ant sting so excruciatingly painful. Has anybody seen, there's this one guy, I only know this because my boys like watching this stuff, but he goes to tropical places and he purposefully allows insects to bite him to see what's the most painful. And I guess he has, like a medical crew with him in case he goes into shock and stuff. But solanopsin is essentially a venom that the fire ant here, this big ant, will. I don't know if you can see it here, but there's a drop right there. See that little bubble? That's solanopsin, and now it has a drop on that antennae of that. That is a tawny crazy ant, and both of these ants originate from South America and have overlapping territory, and so they fight. They're very territorial, and they've migrated up to the U.S. They're here now, I think, in the southwestern portion. And what solanopsin does is it is hydrophobic, and it digests. So it being
it's hydrophobic, so it can digest the cuticle. Cuticle is like this waxy covering on the outside of the ants. And so like dissolves like, and essentially breaks down their protective cuticle, and then it enters in their body and is a really potent neurotoxin.
Didn't the fire ants have like a way to protect themselves from that?
Well, it's the fire ant injecting it into the tawny crazy ant.
Yeah.
So yes, that's where I'm getting. Thank you for the assist. Yes, so the crazy ant has formic acid. You might remember when we were talking about this, I mentioned that formic acid comes from the word formica, right? If you squish, I've been squishing a lot of ants lately because they've invaded my home. Not just the little ones, now these big ones too are coming in. But yeah, it has a really like soury, kind of tangy, sweet smell. And probably taste, but I don't. That's formic acid. That's like their blood that we were talking about, right? Well, so turns out that what these crazy ants will do is they will secrete formic acid on themselves and rub it into the solanopsin. And they don't really know how it neutralizes the effects, but it's believed that solanopsin here, formic acid here, right? This is an amine, very basic. Formic acid, a very weak acid, but because it's such a strong base, just like over there, right, with acetic acid, it can deprotonate and then alter the solanopsin by just adding hydrogen onto it, right? Which is remarkable, right? That we take nothing else has changed, right? It's not like it breaks down the toxin, right? It simply makes the nitrogen a little bit uncomfortable, right? It puts a positive charge on that nitrogen, and that is believed to be the effect that they have. And there's I put a little YouTube video here, which you can watch. Is there sound? How do we do sound here? Maybe there is no sound. So I will be the narrator. So here's the big fire ant, right?
Yeah.
Actually, this probably looks better over here. And these are the tawny ants. That's really blurry. Why does that look so terrible? But they're fighting. Okay, they're saying, no, this is my turf. No, my turf. And it stings it, or it squirts it essentially with that solanopsin. And what's going to happen is they're going to have a clip later on where the tawny ant, now look, this is what it's doing. It's grooming itself. So it's taking its formic acid and it's essentially coating itself to neutralize that toxin that the fire ant squirted on it. And so rather than having its cuticle digested and it's essentially, there we go. So simple, quick video, but rather than being then killed by that, it lives another day. All right, so that's all the cool stuff. Now we got to get to the business stuff, right? How do we name these? Well, we just put amine at the end. With primary means, that's a secondary amine. But it's very similar to alcohols, right? In that the alcohol takes precedent in the parent name. Now, later on, we'll talk about, we have a disubstituted benzenes or other cyclic compounds. Depending on what else is on there, the amine may pop up to be a substituent instead of a parent. But here, all we have are hydrocarbons, so it's going to be, you're going to count the longest chain, and in this case it's 7, so that's hept, so heptanamine, not heptamine. It's like heptanol, only it's amine instead of all, so heptanamine. And of course we have stereochemistry here, so we need to add that in for the amine group and that methyl group. And then just put in our dimethyls. So this compound looks very much like the alcohol and is named similarly as well. Okay. Okay, here's a graph from the OpenStax, and again, aesthetically not as pleasing to me, but we have a lot of heterocyclic amine compounds, and they have their own kind of special names. I'm not going to have you memorize all of these, but pyrimidines in particular are important for us because our nucleotides, 50% of our nucleotides are pyrimidines. The other ones are purines. And so purines and pyrimidines come together, and we'll talk about that in a couple weeks from now. But you can see they have all different types. There are bicyclic compounds here and here, the quinoline and the indole. And indoles are also very abundant in life. So just examples of this. And these are, of course, their common names. We could come up with IUPAC names for them as well, but they've been called this way before IUPAC. So just like so many other things, these are the carryover names, like aniline, right? All right. So here is an example where, let's see, is there something in there? Yes. So here's an example of when we have more than one substituent on that molecule, then how do we name it? Well, if in this case it's an alcohol, the alcohol becomes the parent, okay? It also is gonna take preference on the numbering, right? Because we always want the parent to have the lowest number. So this would be 1, 2, 3, 4 amino butanol. This here, right, we know this is aniline. We talked about that when we first started talking about substituted aromatic compounds. And then if we have something like chlorine, right, we can keep this as the parent, right? So we can call this metachloroaniline or 3-chloroaniline. Another case here, benzoic acid is going to take preference over the amine group. Right? So things with alcohols, we'll give them the parent. All right? So this would be a benzoic acid with an amine group, not an aniline group, with a carboxylic acid. So those you will, this kind of thing I do want you to know. And it's a good idea to know what aniline is. Okay, so benzene, aniline, nitrobenzene, toluene, xylene, those are things that are pretty common in OChem. And then, of course, when we are having multiple substituents, the halides do not take precedence over the amine group in terms of the parent, all right? And we're going to try and minimize the numbers, right? So we would do 1, 2, 3, 4, 5. 5 ethyl 2 fluoro. We wouldn't go clockwise. We would go 1, 2. It would be 3 4, 5, 6. It would be 3 ethyl, 6 fluoro, right? We want to keep those numbers as low as possible, just like you've been doing all year. Okay.
So you have to kind of use numbers there. You couldn't be like ortho meta because they could
No, I
two
mean,
different
so you,
combinations.
because it's ortho and meta is always going to be in relationship to like to the aniline or whatever substituent. And there's too many here, right? You mean would you call it like ortho, fluorine, meta, ethylene? I've never seen 2 in the same name.
Okay. Because it could be in between, or it could be on the other side, the fluorine.
Yeah. Yes, I mean, cool. So if I just said ortho fluorine, well, it's like, okay, well, is it here or here?
Okay.
Right?
Yeah.
Here, these are para. So I think it'd just be too confusing. I could see a way where maybe you say ortho fluorine, meta, ethyl, and then in parentheses para, showing that they're para from each other.
Oh yeah.
But
Yeah.
it's easier just to give them numbers in this case.
And then if there's 2 substituents, it's still okay to use numbers instead.
Yeah, I
of
mean, honestly, for me, the easiest thing is to do IU,
yeah.
right? Rather than deal with common names, there's always going to be an IU packaging, right? And for this, yes, you could call that meta, or you could call that 3-chloro.
Okay.
And 3-chloro would be just as legitimate an answer as meta.
Okay.
In fact, I would say it's more contemporary, right? The meta, para, ortho are older systems that have stayed, again, carried over from the pre-IU pack naming system.
Okay.
All right. So, another example, right? Here, we could call this ethyl, methyl, propyl, amine. So kind of like how ethers, where you have the whatever groups are on either side of the oxygen, we would put that in the name. With an amine, we can put however many groups there are, and it looks like here they have them alphabetized. Right? So again, if you said methyl, propyl, ethylamine, that I could get the same answer, right? It doesn't matter alphabetically, but in the true purest sense, we would alphabetize them. I don't care so much. If it's the same group on either side, then we can use our prefixes, di, tri, and that would be like this, diethylamine. Methylamine, that's just the methyl group on an amine group. And I don't know if you guys remember, but several years ago, by several, probably 10. The older you get,
Yeah.
several becomes like, it feels like it was 3 years ago, but it was actually longer. There was methylamine contamination, maybe it was like 15 years. Dog food had methylamine contamination. That dog food that was produced in China, and it was a big, big deal because it was toxic to the poor pups that were eating this food. Methylamine is also in certain types of plastic dishware often. It makes them hard and sturdy. So methylamine is in there. So trimethylamine is just 3 methyl groups, right? And then now we're getting more and more complicated, right? But again, you look at the
this chain, there's going to be 6, right? And then we want to keep those numbers down. So in this case, we number it from left to right rather than right to left, because that would make these numbers higher. But we'll have stereochemistry, right? So S, and then 2,2-dichloro. And then remember that the N is the locant. So if we don't need to put N here because we're saying that there are 3 groups coming off of that, right? Or here, it's kind of baked into the name. But when it gets more and more complicated like this, we can't just call this, like if that wasn't there, I guess you could call this ethyl methyl hexylamine. But actually, you could call it maybe 3 hexylamine. But you see how that gets a little bit wonky, and now we have chlorine on there, so what we do is we just break it down further, right? So we add the N as a locant, saying, okay, there's an ethyl group coming off of the N there, and a methyl group coming off of the N. And then that's going to be on the 3rd carbon, so 3-hexanamine. And then, do we all see why this is S? So S would be counter, right? And if we're looking at this, what's gonna be number 1?
Nitrogen.
Okay. What's gonna be number 2?
The chlorine. So
Okay. And so then this is 3. So that's kind of, but what's coming out at you?
nitrogen.
Yeah, so then that means the hydrogen is going back, so we don't need to flip it. So 1, 2, 3. All right, so the nitrogen is going to take priority, and then the halides, and then just that order, alkyl. All right, so let's practice. I'll let you guys work on this one. Stereochemistry in here. All right. So here are the steps, or here, or actually you can see them on your sheet. See if you can come up with a name for this. All right, we get it? Okay.
So, doesn't really matter what kind of order you like to do with this, but I like to find the longest chain. So I'm going to number it this way because that's where that amine group is. 1, 2, 3, 4, 5, 6, 7. So hept. And there's no other substituents other than this methyl group here, so we can call it a heptanamine. So heptane, heptanamine, okay? And then it's going to be on the third carbon, right? So it's 3-heptanamine. And then what else? We got to put the methyl group on there, right? And we got to put the locant. So in this case, I think typically the locant comes first over just carbon-based substituents. So in this case, they did D, E, M, right? For this, we have M, right? And this is going to be an N-ethyl E. So if we wanted to be purist about, did you see that? I just flipped that and caught it, like reflexes like a cat. It's all the coffee I drink. The amines. Okay, 6-methyl. And then this is that's an ethyl, so ethyl, N-ethyl, 6-methyl, 3-heptanamine, anything else?
The R stereochemistry.
Yeah, so it's R, so you're saying 1, 2, 3. R, that makes sense because this group is bigger than that group, so it's not going to go there. Nitrogen takes precedent. So R, well, this one's it's on its way out. Let's see what this one is. That's better. So R, N-ethyl, 6-methyl, 3-heptanamine, right? Does that look right? Yep. I think we're good. Okay. Great. Well, hopefully you got that. If not, hopefully this makes sense. Let's take a break. Take a 10-minute break.